Since action and reaction forces are equal and opposite, why don't they cancel to zero? To answer this question, we have to consider the system involved. A force acts on the orange, and the orange accelerates to the right. The dashed line surrounding the orange encloses and defines the system. The vector that pokes outside the dashed line represents an external force on the system. The system, the orange, accelerates according to Newton's second law. The force on the orange provided by the apple isn't canceled by the reaction force on the apple. The orange still accelerates. The force is provided by the apple, which doesn't change our analysis. The apple's outside the system. The fact that the orange simultaneously exerts a force on the apple, which is external to the system, may affect the apple, but not the orange. You can't cancel a force on the orange with a force on the apple, so in this case, the action-reaction forces don't cancel. In picture A, action and reaction forces cancel. In picture B, when the floor pushes on the apple, the reaction of the apple's push on the floor, the orange apple system accelerates. When the force pair is internal to the orange apple system, the forces do cancel each other. They play no role in accelerating the system. A force external to the system is needed for acceleration. Inside a baseball, trillions of interatomic forces hold the ball together, but play no role in accelerating the ball. They're part of action-reaction pairs within the ball, but they combine to zero. If the action-reaction forces are internal to the system, then they cancel, and the system doesn't accelerate. A force external to the ball, like the one a bat provides, is needed to accelerate the ball. A football is kicked. In picture A, object A acts on B and B accelerates. In picture B, both A and C act on B. They can cancel each other so B doesn't accelerate. When there's one interaction between the foot and the football, the ball accelerates. If two kicks on the ball are simultaneous, equal, and opposite, then the net force on the ball is zero. The opposing forces act on the same object, not on different objects, so they don't make up an action-reaction pair. All the pairs of forces that act on the horse and cart are shown. The acceleration of the horse-cart system is due to the net force, big F minus little f. Will the horse's pull on the cart be canceled by the opposite and equal pull by the cart on the horse, making acceleration impossible? The only concern is with the force that's exerted on the cart system. The net force on the cart divided by the mass of the cart is the acceleration. Now look at the horse system. The opposite reaction force by the cart on the horse restrains the horse. Without this force, the horse could freely gallop down the road. The horse moves forward by interacting with the road. When the horse pushes backward on the road, the ground pushes forward on the horse. Look at the horse-cart system as a whole. The pull of the horse on the cart and the reaction of the cart on the horse are internal forces within the system. They contribute nothing to the acceleration of the horse-cart system. They cancel and can be neglected. To move across the ground, there must be an interaction between the horse-cart system and the ground. It's the outside reaction by the ground that pushes the system. If you hit a wall, it'll hit you back equally hard. If a sheet of paper is held in midair, the heavyweight champion of the world couldn't punch the paper with a force of 200 newtons. The paper isn't capable of exerting a reaction force of 200 newtons, and you can't have an action force without a reaction force. If the paper is against the wall, then the wall will easily assist the paper in providing 200 newtons of reaction force. You can't push without being pushed. That's Newton's third law.